Hello and welcome back to Calculus 3, section 13.3 on double integrals in polar coordinates, or over regions that are described as polar coordinates. So we have had in the past rectangular regions and then general regions. So in 13.1 we had rectangular region, which means that your domain was some sort of the rectangle that was going from A to B and then C to D, and then your shape was built on top of it, and then you had the function x, y, z equals function of x and y. And then we have 13.2, which was general regions, where in the domain we had two functions, G and H. We used G and H. So G and H. So the region was bounded by two functions and the shape was on top. So now you get to again compute the integral, which might have the shape inside. So what we did is we said area integral was double integral over region R dA. So region R would be the shaded region, obviously. Or volume was double integral over region R of the function fxy dA. So we can use double integrals to compute either area, if there is no function inside the integral, or volume, if there is function inside the integral. Because in that case you have function times dA, right? That will be three-dimensional. And we had a lot of examples. The best examples are obviously those that relate to some kind of application or a shape that you guys can work on. So maybe we can take a look at one of these shapes. So let's do this is 13.2. Problem 71 is asking you to integrate this. What is the name for this? Elliptical paraboloid, right? So that's at the elevation 9, and the z equals x squared plus y squared, your x and your y axis and your z axis. So what is the volume? Great. Now, what do we have? Well, if you shine the light above, you will see that we have some kind of a circle, right, in the domain. So this domain here, the circle in the domain, is given with by the equation x squared plus y. I should have picked something that you can see even better than this. Let's see. So domain over here is x squared plus y squared is equal to 9. That's our equation of the circle. So when you look at this, we are supposed to set up, and we're going to use the general region because it's not a rectangle, it's a circle. Now, I always draw domain on the side so I can better understand and see the region over which I'm integrating, because this is where my limits are. So I see that we get -3 to 3 in all directions. I also know that the top one is positive square root function and the bottom one is negative square root function that was discussed last class. So now I get to pick whether I want dx or dy. Well, it's a circle, so it doesn't matter. If you draw dx like this, right, we see that, well, first let me put this, so volume is equal to region R, and then we have our function f of xy in here, which I am going to actually put under a question mark for now, and then dA. I have to address the question mark first. Our shape, well, not our, the shape. So the shape is between two functions. Top being given by z equals to 9, and bottom being given by z equals x squared minus y squared. So you are going to do the same thing you always did in the past, which is top minus bottom. So our fxy must be 9 minus x squared plus y squared. You have seen this before when you did area between two curves, right? This was f, this was g, and then you had the integral of f minus g dx. You also had the disk method, the washer method. Washer method was f squared minus g squared and all of that stuff. So you always had top minus bottom. So now with the 3D shape, it's still the same story. You have a plane on top, which is the flat thing on the top, and then you have the elliptical paraboloid underneath. The shape, the material of this object is trapped between the top and all of this eggshell, say it, that traps it from the bottom. The object is widest on the top in this case, right? And it immediately starts getting thinner and thinner as you go more south. So the top over here is the top, and everything over here is the bottom. So top minus bottom, always the same thing that we had before. So now, if I want to set up the integral, delta x starts at -3 and goes to +3. The bottom of the delta x is always on 9 minus x squared, and the top is always on positive 9 minus x squared. The function that goes inside is 9 minus x squared minus y squared. And we have dy and then dx, because we said that we want to set up a dx integral. If you're setting up a dx integral, whatever you are setting up, that's always the one at the end. So we could have done it in terms of y. The only thing that would change is these guys would be y's and these would swap, because this is a symmetric case. You won't be always as easy or possible to do that. In this case, because this object is awesome, we can. So this is our setup. Yes?
How did you get the square root of
9 minus... Oh, these ones?
Yeah.
They are these square roots that are from the equation of the circle, which is the bound, right, the region.
You solving for y squared?
Yes. You solve for y, that's 9 minus x squared. You take a square root, it's a plus and minus, so bottom gets the minus and top gets the plus. So guys, all of this is, we are still talking, this is review of 13.2, and we are setting up this integral to show what we did in the past, and then if we can do it better and easier. So now we have negative 3 to 3. We integrate in respect to y, that's 9y minus x squared y minus y cubed over 3, computed from the negative, there's a negative there, negative square root of 9 minus x squared, and then 9 minus x squared, and then dx. I'm not sure if you're already seeing that we're going to regret this, but such is life, right? So negative 3 to 3. We have 9 square root of 9 minus x squared minus x squared times the square root of 9 minus x squared minus 1/3 of the square root of 9 minus x squared cubed minus, and now we have the bottom one, which is going to be 9 times negative 9 minus x squared plus x squared times negative 9 minus x squared, and then minus and minus gives us another plus of 1/3 of negative square root of 9 minus x squared cubed. All of that still dx. Let's put these brackets here. So now, you know, work algebra and then keep integrating. So all I did is I replaced each y with what the y limits are, and we have this, right, crazy expression. Well, let's see what we can do with this. So the first one, if I factor out square root of 9 minus x squared, I am left with 9 minus x squared here, and then minus 1/3, and I'm going to put this as 9 minus x squared to the 3/2, because that's what the right exponent is. We'll deal with that soon. Minus, so now I'm going to do the same over here. I'm going to factor out negative, but when I factor out the negative, it changes this negative into a positive. So square root of 9 minus x squared times 9 plus x squared, and then I have the negative will survive over here, so it's minus 1/3, and then I have 9 minus x squared to the 3/2, and all of that dx. So going further, negative 3 to 3, we have 9, what is this? So this is a half exponent, and this is 1, so 1 plus half is 3/2. So I have 9 minus x squared to the 3/2. That's the first one. Minus 1/3, minus 2/3, because I have two of these, minus 2/3 of 9 minus x squared to the 3/2. And I have plus, and over here I still have this square root of 9 minus x squared, 9 plus x squared, all of that dx. I need this parenthesis here. So 1 minus 2/3 is 1/3. So I have negative 3, 3, this is 1/3, 9 minus x squared to the 3/2, minus square root of 9 minus x, maybe I can put that to the 1/2 now, so we are going to try to combine this as much as possible before we attempt any integration dx. Okay, so now I can factor out 9 minus x squared. Let's see, 9 minus x squared to the 1/2, and what's left is 1/3 9 minus x squared minus 9 plus x squared. Okay, looking better. So this is -3 to 3, 9 minus x squared. If you already checked out, looking at this calculation, that's fine, because this is not the way to do this. When you distribute 1/3, you get 3 minus x squared over 3 minus 9 minus x squared dx, and then we have 9 minus x squared to the 1/2 times -6 minus 2/3 x squared dx. Oh, this is wonderful. This is amazing. So now we have to use trig sub, right? It's going to be trig sub. Can I factor out -1/3? If I factor out -1/3, this will be 18, right? Minus 2 plus 2x squared, factor out 2 as well, becomes 9 plus x squared. Okay, 9 plus x squared. So -2/3 in front of the integral. 9 minus x squared to the 1/2, 9 plus x squared. I should have... whatever. There we go. Alright, great. Whew. So all we need to do now is to do trig sub, and then we will have our answer. Yay! Yay for Calc2, right? Now this is a good exam question. For Calc2, don't panic. It's Calc3 over here, everything should be easy, right? I mean, this is easy, it's just messy and long and annoying, so yeah. So trig sub, kill me now. No coughing. 3, and then we put x over here. So this is a square root of 9 minus x squared. So we have a cosine and a sine and cosine. So sine theta is going to be x over 3. X is 3 sine theta, dx is 3 cosine theta d theta. Cosine theta is square root of 9 minus x squared over 3. So square root of 9 minus x squared is 3 cosine theta. Nice. So now all we need to do is to plug this in and we're done, right? No, it's more work. So integral. Now we have our limits. When I plug in -3, we can do it. I mean, So if you plug in -3 into here, you get sine theta to be -1, that is at -3 pi, so it's 3 pi over 2. So negative pi over 2 to pi over 2 when you change the limits. And then what do we have? Square root is 3 cosine theta times 9 plus x squared, which is 9 sine squared theta, and dx is another 3 cosine theta d theta. Beautiful. There we go. -2/3 integral. You know what? Kill this third. So this is gonna be, we can factor out 9. We have a 3 and another 3. 1 3 will die. So we have, that's 2754, so -54 over here. -54, negative pi over 2, pi over 2. We have, in parentheses, 1 plus sine squared theta times cosine squared theta d theta, and this is 2 even exponents, so this is just keeps giving, you know what I mean? It's getting worse, which is great. We have cosine squared theta when you multiply d theta. Let's split it immediately. And the second one is, for the second one we can actually, this is nice. For the second integral we have sine squared theta cosine squared theta d theta. We can actually pull this into a sine 2 theta, and then nice. Okay, good. Alright, so what do I have over here? Cosine, the only way to integrate cosine squared is to have it as 1 plus cosine 2 theta over 2. Integrated, that's not a problem. Now the trick over here, for the other side, who picked this problem? This is awesome. Sine, it's Monday, so I mean we're all up to this, right? So 2 sine, if you square this side, you have to square this side. Well, I already have sine squared, cosine squared. I just need a 4. I can steal that from 54, right? Half of 54 is 27 over 2. So 27 over 2 integral, and I have sine 2 theta squared d theta, and I can again use the power reducing formula to deal with this. All of these limits are pi over 2's. Oh, I don't need this now. I integrate. This is 1/2 theta. 1/2 theta, and I have cosine of integral of cosine is sine, so I have plus sine 2 theta over 4. That's that, from negative pi over 2 to pi over 2, minus 27 over 2. Now this integral I still have to write one more time because I have to go with the formula. So cosine 4 theta over 2 d theta. Remember, it always doubles the angle, right? Woohoo! Negative 54. I plug this in. So this is when I plug in pi over 2 over here, it becomes pi over 4. Sine of pi is 0, so this just dies. That's nice. Minus and minus gives me a plus another pi over 4. Beautiful. And this will die as well because 0. Nice. All right, minus 27 over 2. And now when we integrate here, I get 1/2 theta. And then I get a minus, and this is going to be cosine So it's sine 4 theta over 8, because the 4 goes on and times 2 is 8. Good. From negative pi over 2 to pi over 2. This is pi, so this is pi over 2. So half of 54, so this is negative 27 pi. Minus 27 over 2. Over here, plug in pi over 2, you get another pi over 4. This will be pi over 2 times that, all again zeros. Minus, and then the minus is a plus. Another pi over 4. So that gives me pi over 2. Negative 27 pi minus 27 pi over 2, 27 over 4 pi. So this would be 4 times 27, so 3 times 27 over 4 pi. I don't like the negative. I don't like the negative answer at all. $81 over 81 pi over 4 with a negative. This is probably wrong because of that negative sign, which I don't know where it came from, but I would have to go through all of this thing again one more time. And I hope it's wrong. You know why? Because this is not the way to do this problem. I picked this problem because I see that there is a circle, and when you consider the circle in rectangular coordinates, if you have, let me write this in blood. I hope this is wrong. It should be wrong because it's negative, but you know, I would have to go through the whole thing again. Now, polar coordinates. Now look at this. Why do I hope that my 3 hours of work is and writing all of this is wrong? Because when you consider polar coordinates, circle is given by r equals a number. So r equals 3 is circle that was represented earlier with x squared plus y squared is equal to 9. What is easier to work with? R equals a number or x squared plus y squared equals 9? Right, so I don't think there's any contest between these two. R equals 3 has to win. So polar coordinates, as you learned in pre-calculus and then calculus 2, are supposed to complement the rectangular coordinates, and they're supposed to make our calculations and our life much easier when you are dealing with calculations that involve circles and rounded shapes. Now, what are the other rounded shapes? Well, you have those flowers and cardoids and annuals and a whole bunch of other spiel of shapes that you can deal with that are curved. So if the object has this curvature, polar coordinates might be the way to go. And definitely they are if you have a circle. So now, going back to what you guys already know from Calc 2, you should be able to find the area under the area inside the polar curve easily by working out the equation for or area. So let's go with the, ooh, I spelled Calc2. There we go. There we go. Now I have all the letters in. So Calc2, area was given as 1/2 the integral of f of theta squared d theta from alpha to beta. So this was the formula to calculate area inside the polar curve. And if you have where, let me just put this, where r equals f of theta. So the functions in polar coordinates are given as r equals f of theta, just like you have y equal f of x, right? So that was that. So now, the way this went was, if you have to take the area of the circle, right, you will have this written as x squared plus y squared is equal to some kind of capital R squared. This one converted to polar coordinates was r squared equal to capital R squared, from where r equals to capital R. So lowercase r is the function, the variable r, and the capital R is actually the radius of the circle. So all of this that we did, well, first we had a whole bunch of algebra going, but then we had to do trig sub, because we had to use, right, we were integrating over the square root. And when you have a square root of difference of squares, well, that's trig sub. All of that gets eliminated if you are using polar integrals, because now you no longer have this equation of x squared plus y squared. Now it's just like integrating y equals to 3 or x equal to 7, right? That's technically what we are doing now. So the area would be 1/2 the integral 0 to 2 pi, because you want the full circle. If you want a quarter of a circle, it will go 0 to pi over 2 or whatever. Since we want the full circle, 0 to 2 pi, and then you have your capital R squared, and then you have d theta. Obviously, what you're going to get is r squared pi, which is the area of the circle. But it's so much easier, because in our case, right, instead of this r squared, you would have 3 squared d theta, and that's 9 d theta, and it works out to be 9 theta, and you just compute from there. You get 9 pi quickly as the area without doing this. Now, if you want to, you can also show that we will get the same answer of 9 pi by having the square root on top and square root on the bottom over here with the dx going and so on. That's not the way. What we do now is, instead of representative dx and representative dy, right, we are doing the representative pizza slice d theta. So representative pizza slice d theta is the representative angle, right, d theta, that it's there in the domain, and we are setting up integrals in respect to that d theta. So now, if I have the polar region, and I am dealing with, doesn't have to be a circle. Let's draw something else. Let's go with the cardioid. So let's do this. There's a cardioid. So from the origin, we are going to have this, what we call representative pizza slice d theta. Now this d theta will make its round around the shape. So when I say integral d theta with whatever is in here, the two limits are angles, alpha and beta. Angles. So maybe you start here, so that's going to be alpha equal to 0, and then go all the way around back to the same point you started from for beta equals 2 pi. So 0 to 2 pi in interval notation is the full revolution. Maybe I want a half of the circle, half of the cardioid, half of the flower. Well, if I want a half, then 0 to pi, because 0 to pi is going to trace half of the image. So we are in the control of whether we want the full object or we want the half of the object. If you look at any kind of cylindrical object, you will have a circle in the base. I mean, cylinder, like the bottles that you have, and the cup over here, right, also has a cylinder. So now, I can cut this in half and just have the half of the object. And if I have half of the object, well, that's simply described as 0 to pi, because 0 to 2 pi is the full circle. If I take the sword, right, and cut down half of the object, it will just be 0. I can take a pizza slice. The entire pie large pie has 8 slices before I open the box, right? It's like a Schrodinger's cat. It's called a Schrodinger's pizza, right? Pizza is there, it's not there. Depends whether I open the box or not. Anyway, and probably everyone should get that, but I don't know. Slices, right? So each slice is 0 to pi over 4, because that's what an eighth of a circle is, 0 to pi over 4. Remember that the half of the circle is pi, a quarter of the circle is pi over 2, and then half of pi over 2 is pi over 4. So one pizza slice of angular displacement, right, is going to be 0 to pi over 4. So you are able to cut with this in these polar regions any portion you want, and then build the object on top of your domain, just like we did in 13.1 and 13.2. Build the object on top of your domain by just extending the walls straight up. Remember the stencil, right? So now, if you actually have, if you're into baking or not, and the stencil of a flower, well, we know the formulas for flowers in polar coordinates. It's just simple: sine 2 theta, sine 4 theta, sine 3 theta. So if you have, or cosine, right? So sine or cosine of those. The number in front of sine and cosine is going to give you how. I just had, this is giving me idea for a Calculus 2 project, which is too late. See, I didn't think of this before. If you have it laying around, it could be an optional problem, right? If you have a flower-like stencil for cookies, let's figure out stuff. Because, no, it could be Calculus3 project. Yeah, it's the volume of the cookie and then transition into nutritional value. And you are laughing, guys. These are the jobs. What do you have on every packaging of everything you buy? What do you have? Calorie. Oh, calorie fact. Do you think that someone just guessed that? No, there is someone who's computing the volume of a cookie. All right, and that's you, my Calculus3 students. All right, so because right, the calorie content comes from how much of the cookie you have, right? Bring in some Calc3 into that calculation, right? You don't want to just deal with the average weight of the cookie is. Here, I'll give you the 3 decimal exact answer, right? The precision, 3 decimal. So the number in front of the cosine, well, let's just draw one of these guys. So R equals A cosine 2 theta, A, negative A, negative A, A. How far the flower is going to go out is the number in front of the cosine. And the number of petals is the number in front of the theta. And now that's tricky. If the number is even, then you have twice as many petals. If number is odd, you have that many petals. So if I have 3 theta over here, you will have 3 petals. If you have 5 theta, you have 5 petals. If you have 6 theta, you have 12 petals. So the even numbers double the amount of petals, and the odd numbers keep the number of petals as you see in the formula. So the cookie could look like this. And if the cookie looks like this, this is the equation for its domain. The cookie is going to have some height on top. The bottom is going to be z equals 0. And the top, let's say the cookie is ½ inch tall, right? So z equals 0 on the bottom and z equals 1/2 inch on the top. And you have your cookie. So you have the stencil, right, which is in the shape of a flower. You can measure how big the stencil is, whatever the across is, and then you cut that in half for the number here. You count how many petals your stencil has for your flower cookie, and if you have even number, cut that in half, put it there. If you have odd number, you put that exact number in there. It's very easy to come up with the formula for the flower stencil. Right, and then you can figure out the volume, because now we are going to cover the formula, which tells you how to deal with these things. So right now we are only dealing with area. So is it next lecture? No, it's not next lecture. It's 13.5. So in 13.5 we are going to deal with the volume. Now we're only dealing with the area of the base. And then in 13.5, we are going to upgrade this lecture into three-dimensional cylindrical coordinates, which would be for this particular cookie, or spherical coordinates. Maybe you are going to have a ball, half a ball, and you push the stencil of a flower in it. So the actually, right, if you look from the side, it looks like half of a ball, but if you look on the top of the cookie, it looks like a flower because it was cut in. You can calculate the volume of such a thing using the spherical coordinates. So we'll deal with all of those things, obviously, in 13.5, which is probably tomorrow, right? Today, focus on area only. And that's the area of the domain. I already gave you the Calculus 2 integral to deal with the area of the polar region. But then, the hardest problems we had in Calculus 2 were when you intersect two shapes. So you have a circle and a cardoid intersect, or a circle and a flower and a cardoid, whatever. And then you have to figure out which one is on the outside, which one is on the inside, so you can do the subtraction. Subtraction, the top minus bottom, the left minus right, the far minus close. Actually, that's a better definition, far minus close. You know what? Anytime you have the far minus close, let's do the trick we did before. Let's put that far minus close into another integral so that we can have more. So focus on area only, and what we are going to do now is we are going to define the double integral over rectangular region So now I'm going to say that the double integral on the region R for the function that it's given in terms of r and theta dA is going to be the double integral of fr theta and then r dr d theta. Alpha and beta are d theta limits, and r is going to go from A to B. Now, this is always difficult and tricky now to how to approach this. This is a polar rectangular, which makes no sense, polar rectangular region integral. How can it be polar and rectangular? So, going all the way back to the beginning of the section, we said we have a rectangular region where all of the limits are numbers, and we have general region where the limits of the inner integral are functions. All right? So when you are setting up a 13.1 integral, all of your limits are numbers. And that gives us a rectangle. Now, the wording is now shifting from rectangle being a physical rectangle to rectangle meaning it's numbers in limits. So it's a little bit tricky, and I hope it's not going to be confusing for you to make sure that you are using the... So we have right terminology. We are going to have a polar integral over rectangular region when this is A and B, and polar integral over a general region where these puppies are functions. Yeah. So I'm going to say over here rectangular form again has nothing to do with the rectangle. The shape of this is a flower or the annulus or the cardioid or a circle, has nothing to do with the rectangle. Rectangular wording is purely because we are using A and B, so those are numbers. Compare that to double integral over region R fr theta dA, which is integral alpha to beta, and now function g and h of theta of fr theta r dr d theta for the general. Let's be more dramatic over here, right? So now I'm going to point here into these, good effort, and say general form. Clearly one that it's a general form will be used more than others. Maybe I can box it also this where. So now we have rectangular integrals and we have the polar integrals. Now, when you are looking at this, the question is, what is this calculating? Clearly, both of these are calculating volume, but the focus is on the area in the base, because you have to focus on the setup, because the area of the bottom, right, will calculate this one over here is the region, and this over here is the shape on top. These integrals make our previous problem that we spent 30 minutes crunching, and it's definitely wrong because it's negative 81 pi over 4. this is going to make it into a joke. So same problem that has the shape of the elliptical paraboloid at the height of 9, this being z equals x squared plus y squared. The same problem now becomes a joke, because first off, it's a circle and a base, which is considered a rectangular region, right? And then you have the rest. So let's set this up and see if it makes, and how it makes sense. So here's my domain, xy, and it goes out to 3. So if you are to shine the light from the top on this object, it will go as far out as 3. We know that equation for something like this in polar coordinates is r equals to 3. That's our. So f of theta. Let's not use f of theta now. R equals to 3. All right. I'm going to draw a representative pizza slice d theta. And now I'm going to set up my volume integral for this shape. So I still have 9 minus x squared plus y squared. This is the shape that we have to integrate. And we have r dr d theta. You must memorize the string. R dr d theta is a unit. This is a unit. So that r there is not for decoration. If you remember, the old formula was r squared d theta. So now it's r dr d theta, and one of these r's is your f, and the other r stays in the string. So again, that's the derivation of this is the honors part for the thing. Now I have to look at the. I want to look at the limits. So outer integral corresponds to theta. I want the entire object. Since it's an entire object, it's 0 to 2 pi. So these are the angles in radians. And now I have the radius r. Your measurement for r starts at 0 and goes all the way to 3, because that's as far as r goes. The longest r you have is 3, which is actually r everywhere. Now that changes when you have different objects, but in this case, that's what we have. We have to convert this, and that is equal to 9 minus r squared, because x squared plus y squared is equal to r squared. That's the conversion that you learn in polar coordinates in Calc 2. So now this integral is simply 0, 0, 2 pi, and 3. 9 minus r squared, r dr d theta, and as you can see, we went from having that absolute horror of integral in xy coordinates to integrating a cubic polynomial, which is a joke in comparison. The only thing that makes me happy over here is that I already see that I'm going to have over 4. Our answer was over 4. There will be pi, so at least our answer is good for some partial credit, right? Because we all know all you need to do is to reach the 70, right? And then after that it's smooth sailing, because everything that is constructed at 70% of its full will be good enough. No? Huh? Look at it, 70% completed bridge, which is actually, open for business, will warrant 70% of the charge to go over it, right? Like what's Verzano Bridge, like $20, right? So clearly savings if you are, you know, charging only 70% of $20. Right? It's all about that savings. And 70%. Anyway. What was the saying? C's get degrees, right? The ultimate wisdom. Until you start working. They're asking 100%, not 100, 150% completion and stuff. Anyway, you don't have to worry about that. That's clearly not. It's clearly not important for education. It's just. Let's pass Calc 3 now. 0 to pi. I have 9r squared over 2 minus r to the 4 over 4 from 0 to 3 d theta. Guys, this over here is going to give you negative 81 over 4, which makes me happy, but I also see that the other will be wrong. Yes?
How did you get 9r minus 1?
This is r?
Whee!
Yeah, okay. Right?
Yep.
Good. So now, we plug in 3, 0 to 2 pi. That's going to be 81 over 2 minus 81 over 4 d theta. That's 81 over 4. And then we have integral 0 to 2 pi of d theta, which is 81 times 2 pi over 4, which is 81 pi over 2. This is the answer we were aiming at. What we got with the other calculation is negative 81 pi over 4. So you see how wrong the previous calculation was. And no, I'm not going to go and look where the mistake is. I just know it's wrong. First off, it's negative answer, and you're looking for volume. Let's not have negative volume. The second part is we see with the calculation done right, which is in 2-3 lines, if you use polar, right, rather than all of this. For the same problem, right? Look at that. Amazing. So if you really want to feel good about yourself, go back into my calculation up there and figure out what's wrong. That will give you the kick. If not, then you can at least enjoy the fact that you will always be smarter than anyone who claims that the Earth is flat. There's always that to fall back on every time. That's good. Which actually reminded me that the polar coordinates are the base of the argument that these people are using to say that they're calculating. Anyway, let's go back to the problem. Yes. Well, we are going to So we're going to talk about general regions. So this was an example of rectangular, right, form. And the reason why this is called rectangular form is because we were integrating over a circle, and r for the circle goes from 0 to 3. There is no variation in that. Now, when you are dealing with polar coordinates, right, the circle is a steady r going around. So radius is measured, let's say, from 0 to 3, right? So it is, you have the radius, right, pinned at the point, and then it makes the circle around. So it will make the full circle at always the same. But you can have a lot of fun with these. Sure, all the circles, the flowers and cardoids and everything else. But you can also say r equals theta, right? If you say y equals x, it's a 45-degree line. But if you say r equals theta, you get a formula for a spiral, right? Because when r is equal to 0, theta is equal to 0, you are at the origin. as soon as radius starts growing in time, the angle will progress in time. So they both grow together and you get a spiral because they both grow together. So the way to mathematically represent a spiral is to say r equals to theta. So a lot of cool things that you can do in polar domain that you haven't discussed or considered earlier. So now, anytime when you are integrating over a circle, well, that's your general region. So technically, the first integral is only good for circles and also annuals. If you have something that it's like a pipe, that it's hollow inside, so you have two circles, right, that are, so you have, if you have two circles, so there is a thickness to the object, then you will have the inner radius r, which would be your lower limit, and your outer radius r, which would be your upper limit. So technically, if you're dealing with the rectangular form, you are dealing with circles in your base. So let me, so circle and another circle. So this is a capital R. So inner is capital R1 and the other one is R2. So I would have the volume to be integral from alpha to beta, R1 on the bottom, R2 on the top, f of r theta, r d theta would be something to consider if you have a pipe of some sort. Now, guys, when I say pipe, don't dismiss it as, oh, I am not going to be a plumber. Because trust me, plumbers don't consider this. They just go and they make a ton of money. All right, they don't waste time with these things. They actually go in, they make lots of money, and they leave. Right? They go home and enjoy the rest of the life. So don't disregard when I say pipe, because some of you might have some interest in biology or medical application, and you might want to learn about the blood vessels, and all of a sudden, what is a vein where the blood goes through? Well, of course, it's a pipe, all right, which has the thickness of its walls, right, made out of cells. So you want to think about that type of a pipe, right, and then maybe material sciences and things like that to put a rubber coating around the wire, right? So, guys, there's just so many applications. When something is, you should consider what the thing looks like and where it would be used. All right. So, whatever this is, it doesn't have to be just a PVC pipe for sewage. All right. It could be anything else, and to find the volume of the object, i.e., how much material it has, you will have to use the integral above, unless you want to, go crazy with the calculation we see before. Now, when we go more towards the general case is going to focus on working with two different shapes. So if you have, let's say, a shape like this to consider, and then there is some, so this is domain, we call that region R, right? And then there is some kind of an object, right? So this is the shadow. When you shine the light above the object, this is the shadow it casts. So this is the region over which you are integrating. So now the question is, what is the rest? Right? What am I going to do here? Well, sure, you might be looking into, maybe I have a parabola like this that goes forever, and then another parabola that goes like that, and then this shape over here might resemble the shape that you have. Sure, that's a possibility, right? The same thing, you can make a Nike symbol, right? If you take one parabola, you put another parabola. I actually had that as a project for my pre-calculus class to figure out that, and also in Calculus 2 for area between two curves. Figure out the, right, that's one of the project questions. Right, fit whatever parabolas best go through this and go on and calculate. But also, what we can consider is a circle that has the flower inscribed right there. You see that shape right there? There it is, right? So there's that. And now the question is, what is the setup for something like this? We don't need any of this stuff over here. None of this. But it helps us set up the integral for the region that we do need. Now, when you draw your representative pizza slice, you see that the function on the outside is r of theta, and that's R2, the one that is further your G and H for general regions. So if I want to set up the integral now for volume, it's going to be whatever angle alpha is here to whatever angle beta is there, which is a simple intersection. Simple in this case meaning you will have to go and compute trigonometric equation, right? Solve trigonometric equation to calculate alpha and beta. So we have alpha and beta. Then we have our R1 of theta, which is the circle. Then we have R2 of theta formula, which is the flower. Whatever the shape of the object is on top of this domain, r d theta. That's the way you deal with this. With me saying this, the lecture is over. Now we just do examples. So it's the same thing we did so far, except now in polar coordinates. So you have to solve trigonometric equation instead of rectangular equation and all of that stuff, but it's still, all of that is still doable. So let's go and take a look at examples of this. If you take a peek at the pages with problems and you take a look at all of the shapes that are given there, what you see is why you needed 13.3 for your project, right? What is the problem number 2 on the project? Yeah. Remember what you're supposed to do. You're supposed to boil the egg, trace the egg on the paper somehow. We'll figure out how. On a square grid, and then use the squares to figure out the equations that will make an egg. Egg is not the same on top and the bottom, right? So you will figure out which formulas you want to use to have the top portion, the bottom portion. And then once you have the equation, you can go and deal with, when you have the equation, you can go and deal with setting up the integral and dealing with everything else. So clearly problems 19 and 20 will be very, very helpful to you to figure out and deal with that. All right, so let's set up and solve one of these problems. Problem 11, as you can see over there, is the problem I already did, except this is upside down. So you have r on top and then minus 4, which would be on the bottom, and we had 9 minus r squared. So, you know, flipping those two should not be an issue. Let's see if we can find something that is different. So that's the same. These ones you will do later. Alright, so here are some cool problems. 29, 30, 31, and 32. They're all given as rectangular problems. And as you can see, just imagine how wonderful it would be to integrate e to the negative x squared plus y squared over 2, right? Now, when you consider it that way, of course, it's impossible, right? It's crazy. But then when you go into a polar coordinate domain and you realize that x squared plus y squared, guys, this is a very important skill. When you go into a polar domain and you realize that x squared plus y squared is r squared, and you have e to the r squared, which you still can't integrate, you look at the polar integral and you remember that there is the r, the theta string. Tell me. Do sub. You have e to the r squared and you have r from the string from the polar. It becomes a joke. It's impossible to integrate in rectangular coordinates, and it's a joke of a basic u sub in polar coordinates. So let's do problem 29 because it looks so bad, but it's actually so easy. They're called the island problems. They give you the terrain of some sort, so they give you the equation. Guys, the equation that you see there, the e to the negative x squared y squared, e to the negative x squared equation is the bell-shaped curve equation, which is why statistics programs do not transfer basic statistics. It's not calculus based, because in basic statistics you look at the chart for z-scores to get the values, where in the calculus based statistics you get to compute them as the improper integral of negative x squared. So there's that. All right, so we have some kind of a shape over here, which is given to us as so this lives in the xy plane, and this shape has the equation z equals e to the negative x squared plus y squared over 8 minus e to the negative 2. So that's the shape which we are supposed to integrate, and that's that. Now we want the full thing. If I want the full thing, obviously I'm going to go from 0 to 2 pi on the polar region. As I am setting up the volume, sure, I have to integrate over polar region R. Now, polar region R over here is just a circle. And I have the e negative x squared plus y squared over 8 minus e negative 2, all of that dA. So question is, how far does this circle go? Now, we should be able to calculate that by equaling z equal to 0, right? But we're not going to do that until we convert this into our polar form. And then you will quickly see that the inner integral is supposed to be r dr, right? So your limits should be r1 and r2. Well, when you convert this to polar coordinate and you set z equal to 0 because you want to see what happens at the floor where z equals to 0, you will get your r's. Great. Let's go. Convert this. This is simply going to be e to the negative r squared over 8 minus e minus 2. So that's what your z now is equal to in polar coordinates. So now, to get the limits, we say z equals 0 because we want to see the object is the fattest when it's on the floor, right? So that's why we calculate z equals 0. So we have z equals 0. This is going to be e minus r squared over 8 minus e negative 2 equals to 0. From where e to the negative r squared over 8 is equal to e to the negative 2. E is equal to e, negative is equal to negative, so r squared over 8 is equal to 2. R squared is equal to 16. R is equal to 4. Don't go positive negative 4 because distances are not negative. This is radius. So limits are 0 to 4. Volume is equal to 0 to 2 pi. I want the entire circle. I just calculated 0 to 4 on limits for r. I have the equation e to the negative r squared over 8 minus e to the negative 2, r dr d theta. We are all set up. All we need to do is to compute it. Zero to 2 pi, and now we use u sub. For the u sub, I have that. Should I go with everything? Yeah, what the hell. U equals negative r squared over 8. So du is negative 1/4 r dr. So I don't have a negative 1/4. So if I put negative 1/4, I have to put negative 4 in front. So there should be a negative 4 in front. And then the inner integral becomes e to the u minus e to the negative 2 du. Oh, I forgot the integral. Oops. There we go. Du d theta. Now the limits were 0. That limit of 0 remains a 0 because when you plug 0 in here, you get 0 divided by 8 is 0. And now the upper limit was 4. That's negative 16 over 8. It's negative 2. Now I like negative 2 as the upper limit because there's a negative over here, and we know that when we swap those limits, the negative in front disappears. That's Calc1 theorem. So now I have positive 4 integral 0 from negative 2 to 0 to pi, and now we just have to integrate, and it's done. So a little bit of mathematical gymnastics, but not that bad. Integral of e to the u is e to the u minus e to the negative 2u. That's, guys, this is not a function, it's a number. It's 1 over e squared. 1 over e squared is about 0.1. So that's just a number. So when you integrate a number, it picks up a variable. So, you know, when you integrate 3 dx, you get 3x, right? So when you integrate e to the negative 2, you get e to negative 2x. So that's why it just picks up a u. We have from negative 2 to 0, and we still have d theta to deal with. It's a double integral. So let's go and calculate. So e to the 0 is 1, minus a 0, that dies, minus e to the negative 2, the lower limit, and then minus from the formula, minus from the equation, minus from there. That's 3 minuses in a row, 2e to the minus 2 d theta. So this is 4 integral to pi. I have 1 minus 3e to the negative 2. I could just write what this is 3 over e squared, guys. If it's going to be easy, this is just a number. There are no variables here. It's all a number. And now, when you integrate, this picks up a theta. So you have a 4, 1 minus 3 over e squared times theta, which is computed from 0 to 2 pi. So it's just going to pick up 2 pi. This is 8 pi, 1 minus 3 over e squared. And this is the volume. That's the exact number. You can go and you can get the decimals if you want. This problem cannot be solved in rectangular coordinates at all, right? Because you can't integrate. You don't have enough material for u sub, because when you set up this integral, if you were to set up this double integral in rectangular coordinates, you would just have e to the negative x squared y squared, and then dx dy. So there will be no extra x, no extra y for u sub. And you know, you would have to go into trig substitution, but then trig substitution would be an exponent of just no, right? There is a way to deal with it, but it takes complex values, and then it's going to be obviously more mathematics, more courses to deal with. So that's the polar coordinates. You have the polar coordinates, and then you will just have to be careful with what type of the domain you have. If your domain is circle or 2 circles, then it's general region. And if you have the some kind of functions in there, so flowers in combination with anything, or the cardioid or whatever, then your general region becomes, right? Break time? Or one more problem? Problem or break? Break? All right. That ends it then.